Hello, everyone. Thanks for watching. So in this video, I'm going to discuss what is Taylor polynomial of order n. So what I have here is a Taylor polynomial of order n generated by this function f of x centered at a. Now, if you were to recall what is a Taylor series, so we know that Taylor series is a power series centered at anywhere really, going from 0 to infinity. So I can express a function f of x as the infinite sum. So starting from 0 all the way to infinity, the function take its nth derivative, evaluate it at the centered, which would be a to keep things consistent, divided by n factorial times x minus a to the n power. So that will be the Taylor series. It goes all the way to infinity. Now, instead of going it to infinity, we're going to stop at some value. Let's say k or n, really anywhere. So if you want to make this look just like the slide I have up here, we're going to modify this and change the n to k. That's just a dummy variable. We let k start from 0 all the way up to n. So we stop at n, and then we look at the derivative of the function of the kth order evaluated at a divided by k factorial times x minus a to the k power. Again, n and k are just dummy variable. I changed them so that way this looks exactly consistent with this slide right here. Now you can write out the terms all the way up to n, and that will be this term right here, the last term. So that tells you the order of the polynomial. Since you're going all the way up to n, this will be the polynomial of order n. Now let's go ahead and take a look at an example. Let's say I want to write down Taylor polynomial of order 2. So if I want to write down Taylor polynomial of order 2 for any function, then all I have to do is write out this term, and that term, because the power of that last term is 2. So that determines your order or the degree. So if you were to expand this summation, what you're really doing is summing up from k equals 0 all the way to 2 of f to the kth derivative evaluated at a over k factorial times x minus a to the k power. So we're only going to sum up to 2. So k is going to go from 0, 1, and 2. So if you write them out, so when k equals 0, you're looking at the function 0th derivative, so there's no derivative, the function at its center over 0 factorial, which is just 1, x minus a to the 0th power, that's also 1. So that's the first term. Plus, now when k equals 1, you have the function at the first derivative evaluated at a divided by 1 factorial times x minus a to the 1 power. Now I want second order, so I need to go for one more. So this will be plus the function evaluated, the second derivative of the function evaluated at a divided by 2 factorial times x minus a to the second power. So that's your Taylor polynomial of order 2. If you want order 3, you go to the next term. Order 4, you go out to the next term, and so on. Now let's do an actual example with an actual function, and we select the center. So here's the function. F of x is 5 over 4 plus x. We want to find the third degree Taylor polynomial for f of x centered at 2. So previously I used a for the center. Here I'm using x naught. Again, they're just dummy variables, so don't be confused by that. So what we need to do is we need to find the Taylor polynomial of order 3 of x. So that would be the function evaluated at 2 plus the first derivative of the function evaluated 2 over 1 factorial times x minus the center, which is 2, to the first power, plus the second derivative of the function evaluated at 2 over 2 factorial times x minus 2 to the second power. One more because we need third degree, so the power has to be 3. So this will be the third derivative of the function evaluated at 2 over 3 factorial times x minus 2 to the third power. And that's it. That's how many terms we need for a third degree polynomial. So now the key is to compute these guys right here. And then we just plug them in. So we're going to use some differentiation technique from previous calculus courses. So this function, you can write it like this. So if this is f of x is equal to 5 times, then I'm going to bring this on the numerator. So there'll be 4 plus x to the negative 1 power. So we can use some chain rule and power rule to differentiate. So let's find the first derivative of x. So you bring down the power, subtract 1 from the power, and then use the chain rule, differentiate the inner function. So this will be negative 5 times 4 plus x to the negative second power times 1, because the derivative of the inside, which is x, is 1. I'm not going to write that since I think we got that far. So this is good. If I simplify this, this will be just 5 over 4 plus x to the power of positive 2. So I can just write it like this. I'm going to evaluate them a little bit later. Let's compute up to the third derivative. Then the second derivative of f of x, it's going to be, so I can differentiate this because it's easier to look at. You bring down the power, subtract 1 from the power, and multiply by the derivative of the inside. So this would be 10 times 4 plus x to the power negative 3. So this would be just that, times the derivative of the inside, which is 1. Again, I'm going to rewrite it like this. This is 10 over 4 plus x to the third power. And then one more to go. So the third derivative of f of x, it's going to be, again, bring down the power. So that'll be negative 30 times 4 plus x to the negative fourth power times 1. Again, I'm ignoring that. So this is negative 30 over 4 plus x to the fourth power. All right, so that's the maximum derivative I need. So we can stop here. Now let's evaluate them at 2, because our center is 2. So the function, so here's the function evaluated at 2. So f at 2, that's just 5 over 4 plus 2. So plugging in 2 into the original function, that's 5 over 6. So that's my coefficient for the first term, a sub 0, or f of 2. Then this one will give me the next coefficient, which is the derivative at 2. That would be negative 5 over 4 plus 2, that's 6, so 6 squared. I'm not going to simplify them. You can simplify them if you wish to, but this is good enough. Then the second derivative at 2 would be 10 over 6 to the third power. And one more to go, the third derivative at 2, that would be negative 30 over 6 to the fourth. All right, so I have computed all my coefficients. So the first coefficient is right here. The next coefficient is right here. And the next one is here. And the last one is right here. All right, so I'm going to go ahead and erase this so that I can plug in my coefficients that I just computed. But make sure you understand this. So let's see what this looks like. So we have f of 2, well, we found that to be 5 over 6. So this is 5 over 6 plus the first derivative at 2, that's negative 5 over 6 squared divided by 1 factorial, that's just 1. So I can just say negative 5 over 6 factorial times x minus 2. And then the next term is the second derivative, that's this one right here. So I'm going to start erasing these. So the second derivative at 2, that's 10 over 6 cubed times 2 factorial. So don't forget that. And then x minus 2 to the second power. And the last term we're plugging in is the last term I have here. So I'm going to get rid of this. This would be negative 30. So let's put a minus here. Negative 30 over 6 to the fourth and times 3 factorial. So don't forget your factorials. All of these coefficients gets divided by the factorials respectively, times x minus 2 to the third. So there you have it. This is your tailored polynomial generated by this function f of x centered at 2. So you see the highest power we have is at 3. So it's a degree 3 polynomial. Alrighty, so this is it. I hope this helped you understand tailored polynomials a little bit better. It's really nothing new. It's just Taylor series, but instead of going to infinity, you stop at some n, and n could be really any real number. All right, I'll see you next time. Take care.